In Chapter 17, we've been looking at different ways in which we can use and structure tree data structures within a programming language. Any programming language can do tree structures. In fact, most can. It's a principle of the way in which we organize data, not a principle that's associated with a particular programming language. Java, like many other programming languages, implements trees, or you can implement trees in Java as well. We've looked at several of them. We looked at the way in which you can have a tree with many children, a tree with just 2 children being a special case of a tree called a binary tree. If we imposed conditions on that binary tree and said the elements down the left side of the binary tree have to be greater than the node we're currently at, the ones down the right side, left one less, right one more, that's a binary search tree. That's a particular kind of constraint we place on the data that's within the tree. When we have a tree, we know that we can move through the tree in a couple different ways. We can use a pre-order traversal, an in-order traversal, or a post-order traversal. And we also know that if we use a visitor pattern, we can visit the nodes in our tree in a depth-first order or in a breadth-first order. In this lecture, what I want to introduce to you is a different way of constraining the data in a tree that's similar to a binary search tree, but is slightly different in the way in which it organizes data. And this data structure is called a heap. Now, a heap is built on top of a tree, but it has a particular characteristic that makes it's a particular thing that's true about this tree. And what's true about this tree is that at every node, the data that's stored in that node is smaller than all of the data that's below it in its children. So you can think of a binary search tree as kind of ordering data kind of from one tree through the middle to the right side tree, so kind of child center right maybe. But a heap is more ordered top to bottom, where the root node has the smallest element and the children have elements that are greater. Now, it's not really, the children nodes are not ordered in any particular way, but that property holds true on each one of the children nodes, that at any node within a heap, the data that's present at that node is less than all the data that's below it. Now, in particular, this is a kind of heap called a min heap. Min heap because it's the minimum element on the top. A couple properties about it. It is a binary tree. It has a left child and a right child. The other thing about a heap is that it is always a very, very full tree. It's almost always completely filled, meaning all of the nodes and all of the children are filled in except for the very last level. The very last level can be partially filled in because you don't always have a power of 2 minus 1 elements. So we fill in the tree up to the last level, and then the last level fills in from left to right, where each one of the nodes has this node property, which is that the value of the root is the minimum of all the values in the tree. This is kind of what it looks like in terms of that filling in property. This is an example of a tree. We can't tell just from this picture whether it's a heap or not because the data that's in each one of these nodes is not shown. But what this picture is showing you is how we fill in the data in the heap. You can see that we've filled in the top 3 levels, and the 4th level is proceeding from left to right, where we filled in 3 of the elements, but the remaining 1, 2, 3, 4, 5 elements have not been completed yet. As we add elements to the heap, we'll complete that layer from left to right until the bottom layer is full, at which point we'll continue making another layer, the 5th layer, starting from the left as well. Now if you're thinking ahead, you may say, well, this is an odd way to build the heap because it doesn't reflect the way in which it's structured. Recursively, we've only seen trees that are structured like a linked list. Well, the key difference here, and the reason why we can do this, and I'm going to show it to you at the end, is that we're keeping track of this heap, a tree. We're keeping track of this tree in a different way than we keep track of the binary search trees we've seen so far. Just like there's a difference between a linked list and an array list, the way in which we keep track of a heap is more like an array list, and the way in which we kept track of our previous trees was more like a linked list. More on that to follow. Let me drill down into the properties of the heap a little bit more. As we think about filling out the layers of the tree, we can think about it a little bit like completing the levels of a skyscraper. where you have to complete the bottom levels of the skyscraper before you can build layer levels on top of that, because you need that foundation in order to build up. And skyscrapers aren't built with the left side all the way up first. You build it up floor by floor, at least to the degree that I understand building of skyscrapers. So here's an example of a heap in which all the data has been filled out. And what you can see is that all of the integers in this heap, you could keep track of anything you wanted to in a heap as long as it's comparable, but the integers have a very natural understanding of the minimum. You can see that for all the numbers, 20 is the lowest number. And as you look at any particular subtree, for example, the left subtree, 75 is lower than all of the elements below it. It's lower than 90, lower than 84. If you look at the right side, 43 is lower than all the elements below it, 57 and 71. So while the property of a heap is true at any given node, notice that there isn't any constraint about the data from the left side or the right side. For example, notice that on the right side of this tree, there's a 71 on the third layer. But on the left side of the tree, there's a 75 on the second layer. So that's not required. We don't have to have the 71 higher than the 75 globally across the tree. We just have to have within each subtree that property holding. So even as we go down to the left side and we see the 84, 84 is less than 96 and 91. All right, so if we have this property, we can use the heap for different kinds of things. A heap is different than a binary search tree, though. The shape of the heap is very regular. It builds out layer by layer, whereas a binary search tree can have an arbitrary shape, depending on the order in which you put things into that binary search tree. In the heap, the left and right subtrees both store elements that are larger than the root element. But in a binary search tree, the smaller elements are stored to the left and the larger elements to the right. So it's left-right rather than up-down. In a heap, the algorithm that we use to insert data looks something like this. Find the vacant element at the end of the tree. That's the place where we're going to put some data. If the parent of that empty slot has a value that's larger than the element that we're about to put into the empty slot, we can't do it because it would violate the heap property. So instead of putting our new data into the empty slot, we move our parent data and put that into the empty slot. And then we consider putting our new data into the slot that was vacated by the parent. In order to do that, we have to check to see whether the parent of the newly vacated slot is less than the element that we're inserting. If it isn't, then we need to move that parent down and move up one. So we need to start at the bottom and bubble our new element up until it gets to a point where its parent is less than its value. Finally, when we get to an empty slot recursively that contains a parent that is less than the element we're inserting, we go ahead and we insert our data into that particular element. Let's look at what this looks like visually. Here's a heap that exists with a root of 20, and what we would like to do is we would like to insert the value of 60 into the heap. Our empty slot is down there at the bottom as a child of 90 and a sibling of 93. But if we were to insert 60 into that empty spot, it would violate our heap principle, which is that all elements above a node have to be less than a node. 90 is greater than 60, and so we can't put 60 in there. And instead, we put 90 into the spot that is next in line, leaving an empty spot where 90 was. That empty spot where 90 was, we could put 60 in there, but that wouldn't work either because the parent of the empty slot, 75, is also greater than 60. So we bump 75 down to that new empty slot. Now we have an empty slot that's a child of 20. And since 20 is less than 60, it's okay to put 60 into this spot as well. So we go ahead and we drop 60 into that particular slot, and now we have maintained our heap property, which is that every element is less than the elements below it. When we want to remove an element, there's kind of also a recursive process as well. So we know that the root contains the minimum of all values in the heap. And so if we want to remove the root, remove the lowest element, we take that element out and we extract the root node value, and we move the last node of the heap into the root node. So we go to the very bottom and we move that up into the very top. And then we bubble it down. we say, okay, we know that that element is going to be higher than something. And so we look at which one of the children is less. And we swap out the new position in the root with the smaller of the child node. Now we continue with the element that was too big, swapping it out with smaller children until it ends up at a point at the bottom where all the nodes that it's passed by have been less than it. And now the heap property is fulfilled. And we call that fixing the heap. We know we're going to take an element out. Typically, the reason why we have a heap is because we want to take out the minimum element. So we're going to take out the root. We pull the element off the last bit of the heap and we put it at the top, and then we bubble that top element down until the children have replaced it. Here's what it looks like for a particular heap. Here's a heap, and we want to remove the root element. That's the common thing that you do with a heap. You remove the smallest element. When we take that 20 element out, it leaves a gap in our tree, and we go to the end of our heap, the 93, and we put the 93 in that spot. Our heap property is probably violated at this point. And so we have to consider which of the two children, 75 and 43, is the least, and we swap that with 93. That gives us 43 at the top, and now 93 has moved down. And we continue recursively doing that process at the 93 with 57 and 71, swapping the 57 and the 93 until the 93 has until the place where the 93 is either has no children or the children that it has are greater than it, maintaining the heap property. So now the heap has been fixed. Now, what's amazing about the heap is that it always keeps track of the lowest element at the top of the heap, but it doesn't require us to completely sort the data. Inserting or removing an element from the heap is order log n. We know that because we only have to look at one path from the top to the bottom, and for any tree that contains n elements in it, we know that the height of that tree, especially if it's a balanced tree like a heap is log n. So the operations that we've talked about, insertion and removal, at most have to hit log n nodes or h nodes, whereas h is the height of the tree. The tree contains between 2h-1 and 2 to the h nodes, 2 to the h nodes being n. And so we know that the number of things that we're hitting is between 2 to the h-1 and 2 to the h. And so if we solve that, take the log of all components, we see h-1 is less than or equal to log base n, which is less than h. The reason why we're able to do this is because we're going to keep track of our tree in a different way. This regular layout enables us to keep track of it efficiently in an array. And the way we're going to do it is we're going to keep track of our layers sequentially within an array. We're going to leave our 0th element empty, and that'll sort of reflect our root. And then we'll let our first element go into position 1 in our array. And from this point on, we can use the indices of our array to quickly and easily find the children and the parents. So for example, an element in the array at position I has its children at position 2 times I and 2 times I plus 1. So let's look at that in this example tree and the array. Position 1 holds 20, and the children are at 2 times 1, which is 2, and 2 times 1 plus 1, which is 3. So 75 and 43 exist at the child nodes of layer 1. Well, let's think about, what about 84? 84 is at index 4 in our array, and if we want to know where the children of 84 are, we use the formula and we say 4 times 2 is 8, and 4 times 2 plus 1 is 9. So the children of index 4 are at index 8 and 9. And you can see that the children of 84 are 96 and 91, and they are at index 96 and 91. Likewise, we can find the parent of any node by doing the integer division by 2 of its value. So you want to know where the parent of index 10 is that holds the value 93, divide 10 by 2. And the parent is at position 5. And you can see that that holds element 90. So in this way, what our heap data structure is able to do very easily is to add things onto the next layer of the tree. Because all we have to do in order to find the last element is go to the end of our array. That gives us both the spot to add a new element in and it gives us a place from which to remove an element and place it at the root. And then bubbling up and down just entails bubbling elements up and down based on the integer mathematics associated with its index. Okay, so like I said at the beginning, this is called a min heap. It's also possible to have something called a max heap, in which we keep track of the maximum element at the top instead of the minimum element. And this, you can imagine that this is just a pretty straightforward switch from a min heap as well. One of the things that we use a min heap to do is to implement a priority queue. A priority queue is a queue in which every element also has a value associated with it, and the lowest values come out first. Kind of like an airplane boarding line where the frequent flyers get to board first. A priority queue helps you keep track of that kind of a structure. All right, so that's an overview of heaps, and thank you for your attention.